All right, so today we're going to talk about, again, in our kind of series of one-off topics, and this is going to be a one-off topic here. We're not going to get into too much detail, though you could have a whole course on similar things. We're going to talk today about big data and MapReduce. And I like this lecture because it lets me sort of rant about how most people doing big data really shouldn't be using these tools, and you typically shouldn't use them. You should use other things, but if you have to use them, and if you should use them, in fact, you can learn a little bit about how they work. Though, of course, one lecture is not enough to do justice to these things. Okay, so today we're going to start talking first about big data and what I mean by big data. You probably have heard this term, big data, before. It's a very trendy term. Still is very trendy. It's been trendy for a while now. I'm going to talk about what I mean by big data, because I think it's one of these things where everyone says they have big data, right? It's everything is big data, at least from a marketing standpoint. And so I want to talk about what I mean, because I mean something kind of specific when I say big data. And so we'll cover that. And then I'll kind of provide a little bit of context in distributed computing. So this is sort of how, and this is not a history of distributed computing. This is sort of how I see the path of computing and distributed computing evolving as it relates to data science, or how it has evolved as it relates to data science. And people can fill in the gaps or disagree with my personal take on it, but I'm going to give my take on it. Then I'll talk about the map plus reduce architecture, as I call it, right? Which is effectively using functions like the map function and like the reduce function in Python, which, by the way, is quite different, or notably different, from MapReduce, one word, which I'll talk about later, because I think it's best understood sort of in context of first thinking about map plus reduce, then about MapReduce. And then very briefly, I have one slide on how you actually want to implement some of these things in Python, because they're, like everything in this course, there are libraries that do this very nicely. Some quick announcements, as always. Homework 6 was released over the weekend. We were a couple days late. We meant to release it Friday, but we were pushed it Sunday morning eventually. So we'll extend the deadline to account for that. I know we're hitting up against when the project's due the following Friday, but it should just be more time ideally. So you'll have until Sunday, and then you have late days if you want to use them as well. The recitation for the homework will be tomorrow. So there I imagine there'll be even lower attendance than this, but we will record that. Maybe one person can show up at least. But Divya will be giving that tomorrow, probably tomorrow evening sometime, though we have to determine the right place. I think we have like a conference room. It's probably going to be big enough, so we'll figure out the right place and time. And remember, for this homework, so for 388, you do one of the 3 questions. You can do any of the 3. For 688, you do 2 of the 3, and each group can do 1 more for extra credit. So you can get half points doing 1 more. And actually, we're just doing that based upon total points. So you can get if you want, you can get partial credit on 2 or 3, and it's just about total points. So up to 33 points is full credit for 388, and then beyond up to 66 points would be you'd get half of that. So hopefully that makes sense. And the project feedback will be available in a few days. Oh yeah, sorry, question? Worth 1/6? Yes. So this homework, the 1/3 will be worth the same fraction as the normal 2 questions. Yeah. And then the extra credit counts as extra credit on that fraction, which adds to your total points for the homework. Project feedback should be available in a few days to everyone. I'm a bit behind on these. Sorry. Same with tutorial grades. Apologies for being a bit late on them. Have a nice, relaxing Thanksgiving where I can catch up on grading. Okay, so let's talk about any questions on those things before we go on? All right, let's talk about big data then. And I want to talk about big data by kind of thinking about a couple cases here. So let's talk about my laptop first, right? So my laptop has 8 gigabytes of RAM, 500 gigabyte SSD disk, and if you asked, am I doing big data analysis when I do data science on my laptop, most people would say no. Again, that actually, people might use the same volume to say yes, but I think I would argue that that's just wrong. If you're talking about stuff that can fit even on the disk of my laptop, that's not big data, right? That fits on my single machine. It's really small, in fact, just the size of it, right? It's not big data, and it shouldn't be thought of as big data. When you go to the other scale, and so that definitely is not big data, despite what some marketing people may say. On the other scale, you have a Google data center, right? Where I actually don't know how much RAM and disk they have. I think storage-wise, I've heard in the ranges of tens of exabytes for Google. But I think maybe it should be even more than that. And they're not the biggest data center either, by the way. But I don't know how much RAM or disk or how they space this exactly. But regardless, those are big data, right? That is big data. I think no one would really disagree with that. That's big. You have multiple machines. All handling different portions of data, split across many, many disks, et cetera. That's big data. And the question now, of course, is, so where is this magic line about what becomes big data and what is not big data? And I don't want to spend too much time on this because, to a certain extent, the question here is a little tied up with, as I mentioned, the marketing of these things, right? So every company wants to be doing big data. They want to be doing, something that's on a massive, massive scale, even when they're not actually, even when you could fit stuff on a single computer. So rather than kind of talk, I will provide a line, but more than the line, I actually want to point out some sort of important change points or step functions in the continuum of sort of how big data gets. And this is how I think about this. So I think about it is the first case is when your data fits in RAM on a single machine. That's sort of the first category, and that's not big data. I would argue, right? And that, machines can get pretty big, but maybe we're talking about tens of gigabytes here, maybe 100 gigabytes if you have a beefy machine that you can get on Amazon for not too much money, actually. And so that's sort of the tens of gigabytes we're talking about. Definitely not big data. The next kind of step up. And this is not a step just in terms of kind of the quantity, but it's also a step in terms of how you actually have to write programs, right? Because if you can fit everything in memory, you can kind of do what we've been doing all class, which is just sort of apply your algorithms as if you have everything stored in a big matrix or a big array in memory. When you hit the memory limit, though, when you start having to talk about disk, you need to actually make different decisions about how your programs run, because unlike memory, disk is actually quite fast, but it's only fast. Well, certain disks are fast, but they're only fast if you read them sequentially. So they're very good. So not solid state, but normal disks or kind of hard disk drives are very fast if you read them sequentially, but they're very bad at random memory access or random access because they have to actually move a physical thing. SSDs are better at that now, but they still are not nearly as fast as memory. So there is a big step change when you start talking about using or analyzing data that you can't store in memory all at once. And the next big step change is when you can't even fit it on a single computer anymore. And so you need to store your data both in say, RAM and disk on multiple machines now. They just don't fit on a single machine anymore. All your data does not. And the third category here is what I'm calling where your data will fit on disk or RAM in a relatively small cluster. And small here is all arbitrary, but my distinction between small and large is that in a small cluster, you can be pretty confident that no machine is ever going to die, or it's going to be a relatively rare occurrence that a machine will just die. So you can kind of always assume availability of all your machines, right? So you have to spread your data across multiple machines, but you can assume that they're always going to be there. They're not just going to vanish. Which leads us to the fourth category then, is when that is no longer even true. So you think about a data center like Google has. In fact, they were kind of one of the pioneers of this idea because they built very cheap computers sort of early on when they were building their data centers. They used very cheap commodity parts. But in very big systems, if you have 10,000 machines running in a single cluster, the chance of a single machine dying at any given time is actually quite high, right? Disks fail, computers just blow up sometimes, they overheat. And so you have to be able to account for the fact that machines are going to suddenly vanish. And I'm actually fine saying anything that is category 3 or bigger here is big data. I will argue vehemently that categories 1 and 2 are not big data. If you can fit it on a single machine, that should not be considered big data. And anything else is just sort of just marketing. But some people may say it's only 4. You only really have big data if you have to worry about your machines dying. I'm fine saying 3, but it's kind of a continuum, right? And are you better off sometimes putting it on a cluster of machines in RAM versus a single machine on disk? These are trade-offs that kind of blur the line, certainly. But this is sort of how I think about big data. So it's a very useful term, but it's also one that's sort of enormously overused right now. Any questions there? Okay, so the next question that you should ask yourself whenever you start a problem is, do you have big data? When you start a problem that, when you're thinking about using techniques like this, do you have big data? And for the most part, the answer is probably not, right? There is a small range of tasks where the data you collect for this task genuinely will not fit on a terabyte hard drive, right? There are some, but unless you're talking about multiple terabytes of data, you probably really don't have what I would consider big data. You should be doing it on a single machine. You should be using disk by all means, but you don't need to be using kind of the methods that we have here. And there was a great paper in 2015 that kind of made this point, I think, very, very well. So in the past 10 years or so in distributed data science, there's been a lot of different techniques for distributed systems, distributed architectures that supposedly scale really well. So you can add more and more cores, and more and more machines, and they get faster and faster. It's a little hard to read here, but I'll sort of try to make the point here. And so in 2015, this guy, Frank McSherry, who used to be at Microsoft, and a bunch of other people who were former Microsoft people as well, they wrote a paper called Scalability, but at What Cost? And what they showed was they took a bunch of fairly respectable published results from a lot of these distributed computation frameworks, so things like GraphX and GraphLab and Giraffe and Spark. And this is not Hadoop MapReduce, by the way, which these things all, those things all beat the classical MapReduce, which we're going to talk about today. But these things are all faster than that. And they've reported results in the literature about how fast they can solve, say, PageRank, which we know the algorithm, on a graph of a certain size. Or they're also talking about something called label propagation, which is a similar graph algorithm on fairly large graphs. And what they showed was that if they just implement the algorithm on a single thread, on a single machine, that beats most of the published results of these large-scale computational frameworks running on 16 or 128 different cores, sometimes by a pretty heavy margin here. So a certain task here took Spark, running 128 cores, about 900 seconds, where it took a single thread running in RAM, 275 seconds to run. So this is sort of surprising, right? Because people are really, these frameworks are all very popular. And rightly so, because when you start pressing the limits beyond what these things can do, they definitely will scale better than a single machine. But a lot of the actual results, even the ones that are reported in these papers, don't reach the size where you actually need these frameworks. And so the argument was that they're showing great scaling, these frameworks. That they show that as you add more and more cores, you get better and better performance. But what they're effectively doing is adding overhead and then optimizing away that overhead by scaling really well. Right? So so take this very, very seriously. When you start working on, if you go out in the world, start a data science position, there's a good chance you will work on a distributed framework because a lot of companies have these set up. They want to have the ease of use of them. So be very, very careful when you think about these things, about whether you really need it for your task or whether you're just sort of using it for no other reason than it's there. Because very, very often, and they actually publish the code for all these things in a little figure. They're like 10 lines of code in their papers, and that code itself is faster than these frameworks with however many lines of code they have. So really think long and hard about how you really want to, or if you really need a large-scale framework for the size of data that you actually have and you actually want to analyze. And this is also a good paper to Google as well. All right. So that being said, let me provide a little bit of context. Any questions there? It's surprising because we've heard so much about these things, right? We've heard so much about Spark and Graph. And not to say these are bad frameworks. They do handle much more data than you could handle on a single machine. That is absolutely the case. But a lot of reasonable, seemingly large data sets don't actually need them. And they're just adding unnecessary overhead. So they're going to pay a whole lot more without actually getting any benefit. Oh, it was very loud there. So it feels all very quiet all of a sudden. Okay. So then let me take a step back now and provide a little bit of context in distributed computing. So big data did not start with Google, right? Or distributed computing certainly did not start with Google, nor has it started with all these recent frameworks that are making these things very popular. It's been around for a very long time. In fact, since the sort of the birth of computers, people have been trying to say, well, if one computer is good, maybe 10 computers will be even better. Well, let's just hook them up and let's do more work that way. And so there's been a lot of history about distributed computing and going by many names of high-performance computing or supercomputing. But in the sort of the 70s and 80s, this became a real kind of area in and of itself. CMU actually is not one of the most famous, but it's a notable one. The CMU C.MPP supercomputer. I think it's actually, for a while it was in Wien, so you could go see it if you want to take a look at it. It's from the 70s, you could go take a look. It had, I forget what these parts were, but it had 16 PDP-11 processors, and it took up a lot of space in a big room. The most famous kind of first sort of really highly available supercomputers were the Cray computers. So Cray made a kind of a name for itself, building what were at the time very powerful, sort of state-of-the-art computers. The joke now is that this Cray 2, which at the time in '84 was the largest supercomputer in the world, has about the same power as your phone right now. So I actually think that's really impressive for the Cray computer, though. To be honest, that it took us 30 years to catch up with what we can do in a phone for this computer. It's kind of amazing how powerful it was back in the day when you think about it. I mean, your phone can do a lot of things, right? And this thing can have, multiply a matrix at the same speed as your phone. It's kind of amazing. So that was kind of the trend, and really a lot of the applications for these things were what I'm kind of referring to generally as scientific computing. So lots of linear algebra, lots of large scale fluid dynamic simulations, these kind of things, right? It wasn't really so much about data processing, because we just didn't have that much data. There wasn't that much data to actually process, or at least it wasn't in a form you could put into a computer. So a lot of the applications were much more about building simulations of some sort of effect in the world and then analyzing that. That was what the data actually was and what the computation was. And so kind of based around this community, which is kind of generating data, generating simulation results, there evolved in the 90s sort of this consensus that people were developing a lot of similar ways of communicating and executing multiple processes in parallel in these large computers. And so in the mid-90s, people built a common interface called the Message Passing Interface, or MPI. And MPI is essentially a set of tools that lets you run multiple processes over many different machines, or many cores on a single machine, and it provides ways of communicating between these processes. So let's use, for example, transfer data between different processes. And this includes both, what are called scattering data. So if you have a single block of data and you want to shard it amongst all the different processes. Gathering, which is the opposite. It's taking a lot of dispersed things and gather them onto one process. Broadcasting, which is sending a single thing from one to everyone, and a lot of other variants of these kind of sharing protocols. They could also have mechanisms for synchronizing execution. So if you have to wait until every processor finishes some task before you can collect the results, there's a way to sort of block everyone until they all finish a certain task. Then you gather the data, etc. So it provides a nice way of kind of synchronizing execution amongst all the different machines, and it's pretty much a standard right now in the high performance computing community. And it's still very common in these areas, right? So a lot of linear algebra code, parallel linear algebra code actually uses MPI. And MPI is great. I actually like MPI a lot. But I have to say that this has some very large downsides. Has anyone here ever used MPI before, out of curiosity? All right, we have a few people. Well, one person at least. 2 people, great. So it's kind of nice. It's very, very powerful. You have kind of full control over this entire group of processes, but it's really kind of also a pain to use. I see some nodding from people that have used it before, so that's good. It's extremely powerful, but it's also really kind of cumbersome. And the reason is, you need to manage all the communicate. I mean, the thing that makes it powerful is exactly what makes it complicated. It's that you can communicate between all your processes, but you have to communicate between all of them. You can't sort of let them all do their own thing, or sort of have an easy wrapper that provides you. I mean, there are wrappers, but basic MPI means you need to actually manage the data. You need to sort of synchronize all your threads, et cetera. You have to do all that manually, and you don't really have an easy way of sort of automating all of that. And kind of related, but a little bit different, is the fact that it's brittle, too. So MPI is very much in the high-performance computing mindset, where computers don't go down that often. I mean, a Cray, none of the cores would just explode very often. None of the disks would fail very often. It sort of was an all-or-nothing thing. It either all worked or it didn't. That's not quite true, but it's more or less true. And MPI is similar. I mean, you can account for machines dying if you do it explicitly, but you have to do it explicitly then. You have to actually write the code to say what's going to happen if one machine dies. What do I do with the data that I put to that, I gave to that machine before? And this makes it, of course, very hard to scale to the size of problems that we sort of, or size of clusters, say, that we wanted, where we do actually have failures happening sometimes. And so this is kind of the state of things in the late 90s. And then at this time, Google and these companies, similar companies, were arriving on the scene. And Google was doing something very interesting. So Google, there's sort of two important elements about what Google was doing in the context of big data, at least, for this lecture. So what Google was doing was two things. First of all, they were building their data centers out of basically machines you just buy from a store. So hard drives you just buy from a store. Racks you buy, just go out and buy. I think the first one, I was a grad student at Stanford, and they had a little exhibit in the basement of one of the first Google data centers, and it was like built of Legos or something like that, something similar to that. Their racks were built of these things. So they were trying to do it very cheap, which was a great idea because it meant they could sort of buy tons of storage space for much, much cheaper than you would pay if you needed that redundant controller to make sure that you would never lose any of your data, right? They were just sort of building it everywhere with lots of different machines, commodity parts, and kind of trying to mangle it all together. So all of a sudden they had a lot of cheap machines tied together that were very heterogeneous. There were sort of different types, all of them, and they would fail a lot. They had to be able to figure out a way to handle that from within their distributed computation. And the second thing is that they really started moving from this notion of data as the results of a simulation, which really was most data for a long time in computation, right? It came from simulations, not from the world. But all of a sudden now data started coming from the actual world, right? So all of a sudden, the data that was out there was not just generated by a computer. You didn't want to, start a bunch of processes in different machines, each have them generate their own data, and then kind of kill it after it's done. Instead, you had to actually store this data long-term permanently, and that meant that something called data locality is very important. So when you are running a large job that's analyzing a bunch of data, moving data around is very slow, right? Moving data around networks is very slow. And so as much as possible, you want to actually run your execution, your computation, at the place where the data actually lives. So you want to be able to say, okay, if I'm computing a bunch of records or computing a bunch of functions of records on this table, and that table lives on this computer over here, I don't want to first pull all that data to some other computer and execute it and then push back the results. I just want to execute it directly in that computer that has the data, so I don't have to transfer stuff over the network. And both these two ideas led to the development of the MapReduce framework. This was developed in Google. The MapReduce paper came out, the sort of very famous paper by Jeff. Oh, I missed, here I copied it wrong. It's Jeff Dean, and I forget his guy's first name, but Jeff Dean's the first author on that. And Gemma Watt is the second author. I have it later in the slides, I think, so I will cite it properly. Actually, maybe just change this, because there we go. All right, that's better. Proper citation now. And they developed it at Google, and it was, of course, later made very popular by the Apache Hadoop framework, which probably, if you've heard of MapReduce, you probably almost at this point synonymous with Hadoop. But Hadoop essentially wasn't just an open source implementation of MapReduce. It was started at Yahoo at the time, but it quickly became kind of an open source project run by Apache. And it's really, right now, kind of, as I said, synonymous with MapReduce. So this is kind of how the situation evolved. And we'll talk about MapReduce much more in a second. But essentially what MapReduce was a simplification of all the complexities of message passing and distributed computation that existed before into a very simple paradigm where users had to implement just two functions to compute a task. One's called a mapper and one's called a reducer. And we'll talk about what this means in a second. The advantages for Google is that work can be farmed out automatically. If you write these two functions, you can farm out work automatically on a large cluster of machines. As much as possible, you can do this in a way that exploits data locality. So you can do it in a way that actually will do the computation where the data actually is. And the last thing is that things like node failures, or even in a less worse extent, just stragglers, these are sort of nodes that are, for some reason, just seems to be taking a lot more time to compute than the rest of them. These are kind of dealt with nicely. So the execution engine behind MapReduce, if a machine dies, will just spawn up the tasks that was going to run on that machine somewhere else, and everything's kind of kept nicely. So all these things are handled sort of very, very efficiently without the developer, the person writing the actual program, having to worry too much about the details here. And this is sort of a great at the time, and it really, I mean, it's hard to say what enabled the massive uptick in popularity of big data. It probably would have happened without MapReduce, certainly, or with some other framework. But this framework really did, through Google and other places, bring big data and the idea of distributed computation and failure resilient computation. It kind of brought it to the forefront. And honestly kind of left behind a lot of the HPC stuff, the high performance computing stuff that really was the state of the art in distributed computation for a long time. And so since then, this has sort of been a great paradigm for a while. But since then, people have also noted there's a lot of disadvantages to MapReduce. So we'll talk about those in a second too. It's actually, for all its power of being resilient and simple, it's also quite slow a lot of times. And so the way I would characterize this actually is that since maybe 2010, I'm sure it goes on before then, but since sometime soon after MapReduce, the big data community has been slowly trying to kind of look back at what HPC was doing for a while and bring some of those ideas back into the fold, while still maintaining the resilience and sort of the ease of use of the distributed computation we had. We're trying to bring back a little bit of the HPC lessons that everyone knows. And at the same time, by the way, HPCs can sort of humming along just fine. I would have to say that GPUs are kind of the natural outgrowth of supercomputing. And they're doing just fine, right? There's in data science too, right? Plenty of use of GPUs, especially with the advent of deep learning. That there's no lack of kind of the other more traditional vein of large-scale distributed computation. It just takes a different form than it used to. So that's kind of where we are right now. There's the sort of the HPC track humming along. There's the through GPUs and other and also just bigger computers. There's also trying to bring in more ideas like more in-memory management of these large things to the distributed computing, kind of the big data style distributed computing. And that's kind of where we're progressing right now. So the thing I would sort of remember, this is kind of a lesson to when you write your own code, just think about this as a thing to keep in mind. That when you want to know how to solve some task or what's going to be the best way to sort of manage some amount of data, the network is slower than disk, which is slower than RAM, which is slower than cache. And cache is like a small amount. When you have a small amount, sort of like memory, it's very close to the CPU, so it's going to be very fast to access. But basically, it's by exploiting this kind of hierarchy, and there are actually even more hierarchies, right? When you start talking about different levels of cache, stuff like that. But this is the kind of hierarchy you think about with big data. By exploiting that properly, that's going to be the way you're going to make your programs most efficient. And so if you can get away with sort of cutting yourself off here, just do that. If you can do it just here, do that. That's the one machine with a disk. And then only get to there if you really, really need to, and be very, very cognizant of what you are transferring over the network and things like this. Those, by the way, there are certain cases where those can vary. There are some very high-speed networks, et cetera. But for the most part that holds true. All right, questions before we move into the actual kind of content here? Yeah?
In our real life, we are trying to solve some problems, but the data science might not in our own platform. Or what do you think we should go to? Or shall we try to find some extra nodes for computers? Or shall we try some like HPC method or use like C++?
Yeah, I think the question sort of is if it isn't working and you're right on that boundary, won't fit in your machine. What do you do next? And there, I won't prescribe one specific thing over another. You can just buy a bigger machine on Amazon if you want to for a little while and use it for a little while and see if that works. You can try, you can always try to write a better algorithm too, right? This is sort of, but I'm more sort of thinking of the case if the raw data itself just won't fit on your machine, then what do you do? But what I would say is the best situation probably will depend on your type of data. If you have a big matrix to multiply against another matrix, then you want to use HPC machines because they've sort of been developed just for that. Whereas if you have a lot of disparate heterogeneous data sources, you might want to use something more along the lines of Hadoop or a similar architecture. So it really depends on your problem, but there are advantages and disadvantages to all of them. So certainly like GPUs are very fast and they're very parallel, but they don't have a lot of memory. Right? They're sort of going the HPC track, but without a lot of memory. So there's all these different trade-offs that are to be had. And this course is not about that. It's about a brief introduction to sort of how these things work, or how some of the things work. And there are plenty of courses that will get more into that, like the cloud computing course here and others, and a lot of the systems courses here. Okay, so let's talk then, moving on, about what I'm calling map and reduce, for lack of a better word. Because MapReduce is actually quite simple, but for the first time you see it, it sort of seems odd that they're structuring it the way you do. This is MapReduce. MapReduce, one word, seems odd at first, so I want to relate it to something that's even simpler, which is the map and reduce functions that are common to really any language, including Python. So Python has a function called map and a function called reduce. And those functions just do the following. So I'll talk about it in a second, actually. But we can get, so the goal of this is sort of give a quick primer on, or a quick intuition about how these things may work in a simpler architecture. And then we'll move from that to the actual MapReduce architecture, the MapReduce one word. I'll try to always say map and reduce when I mean the map plus reduce functions, and MapReduce when I mean the normal MapReduce. So Python has these two functions called map and reduce. A lot of functional languages have them. They're kind of a staple of functional programming, actually. And the basic idea is the map function takes as input some function and a list, or really an iterable in Python, and produces a list where you apply the function to each element in that list. Right? That's the map function. The reduce function is a little bit more complex, but it's also actually quite simple. It takes a list, and this function g takes two arguments and outputs a single value. And what it does is it will take the first two elements, or you actually can have a 0th element if you want as well. Take the first two elements, it will apply the function, then apply the function to the result of that in the next element, then apply the function to the result of that in the next element, etc., until you get one value or one output out of the whole thing. There's a question there?
Isn't it the case that reduce takes the three arguments, g, the list, and the initial element?
Yeah. So the question was, does reduce take three elements? That was kind of the 0th element I just mentioned. So if you want, you can have a 0th element that will effectively, the first time you don't have this thing here, but the first time you have g of some default element and that, but you can get the same thing by just giving the first element in this list, making that the 0th element. So I'm thinking about the simpler one. What was that?
Might not be so possible like in type languages.
Yeah. So I'm going to talk about sort of just the simple case of this is how, it's just simpler to not worry about an initial value. Okay, so with these two functions, you can do some interesting things. They're quite simple, but you can do some kind of interesting things. Well, by some definition of interesting, I guess. So for example, here's a way that we can take a list in Python. We can square each element and compute the sum of the squared elements. The way we do that is we take our data, we apply a map, and I'm writing this in lambda with lambda notation here for sort of anonymous functions, but this first, that lambda x and then x times x, that was just a function that will square the input and return it. And similarly, lambda x and y, x plus y, that will just add this function will just add its two arguments and return that. So this takes this function squaring the data, squaring the input, and applies it to every element in data. And so values after this will be a list where each element in data is squared. If you apply then reduce with 2 arguments and you just add them together, then reduce applied to that list, or the values list, would just add up all the elements together and then return the output of that. So nothing too amazing here, but a nice function to have nonetheless. And it'll work for any size list, of course. Doesn't have to be doesn't have to be a certain size. Doesn't have to even be a certain data type in Python, but sort of do what you want, right? And it's sort of very, very brief too. I mean, if you had to write a loop to do that, it would be a little bit longer. It just wouldn't be quite as clean. And what this looks like graphically is very simple. I imagine everyone kind of sees what it is. But you basically, the map step, you take your elements, you apply a function, it gets some new value. And the reduce step then starts combining these values to give you some final result here. You actually can do the reduce in different ways too. You can do it like in a tree. But for a single machine, it doesn't really matter. So it's just done sequentially, typically. OK, so now I want to define a little bit more about what I mean by map, reduce, and sort of what's called a mapper function and a reducer function. And I want to define 3 things. And this is actually going to be the same thing's going to happen when we talk about MapReduce, one word. But I want to define this because it's sort of useful to think about these 3 elements to a map plus reduce system, or I guess in later case, a MapReduce system. So I'm going to talk now about 3 different types of functions or entities, I guess. The first is the mapper function. So the mapper function really is just that function f that we apply to every element in the list. The reducer function is the function g that we apply to merge together 2 elements in the list. And what I'm calling the execution engine is kind of the glue that will actually sort of make this thing all work, right? So actually runs the map function and runs the reduce function. And so in the context of the square, summing up a squared list, the mapper function would just be a function that returns its argument squared. The reducer function would be a function that takes 2 arguments and returns their sum. And the execution engine will be the code that you saw before. So that was, I first apply map using the mapper function to my data. Then I apply reduce using the reducer function to my values. It's a little bit convoluted here, I know, but it's going to be useful to think about those different terms. And really, a map plus reduce framework would be all of these components, right? Because you need the execution engine as well as the actual mapper and reducer. But the key point here is that in order to use, so if this thing is implemented as it is right now, and I want to write some new function in my map plus reduce framework, the key point is I only need, if I'm going to stick with this framework, I only need to implement my mapper function and my reducer function. I don't need to write the execution engine. That's going to come in handy a lot when we start talking about more complex patterns for execution. So that's just actually a really key point. So I want to emphasize this sort of very, very, very heavily here. So if I want to now, as a programmer, use my map plus reduce framework, I only need to write to say add up a sum of values squared in the list. I only have to write my mapper function and my reducer function, right? And kind of very nicely, the execution engine can, because that sort of paradigm is very well defined, right? The mappers themselves just operate on 1 element of the list. The reducer just operates on 2 elements of that list. Because that is well defined, the execution engine behind sort of this process can actually be quite complicated. It can do things that are much fancier than just these 2 lines of code. It can actually be quite fancy in what it does. It could do parallel. It could do whatever it wants without me changing any code. I still just write the mapper function and the reducer function. And that really is the key point. So for instance, it's sort of maybe obvious, right? But the mapper functions can all be applied in parallel, right? There's no mapper cares about what anyone else is doing. It's kind of by definition, actually, of sort of this functional paradigm. The mappers don't know what other mappers are doing. They only look at 1 element of that list, and so they can all be run in parallel, in theory. Right? And similarly, actually, though this case is not quite, doing that. You could run the reducer a little bit in parallel too. So for example, rather than doing kind of a linear chain here, I could make a tree where I first reduce and this also assumes certain properties of the reduce function. Those ones usually do hold. I could take that side and start reducing those, and then do it kind of as a tournament style reduce, and that would give you the same result, right? And so the point is that it doesn't really matter how the execution engine runs behind the scene. It doesn't have to use those map and reduce functions that Python has. It will give you the same result, and your result from your code will be the same. And this is a really, really powerful paradigm, actually, as simple as it might seem. So let's talk about now maybe 2 ways we could run the map plus reduce framework. So the first one we've already seen. The first one is a single machine execution engine where we have our data, we apply our mapper, we apply the reducer, and then we get some single value output. I mean, the reducer actually could create a list too. It could append elements in a list. That's fine. So it actually doesn't have to do anything. But I tend to think of it as reducing something, hence the name. And so I think of it as adding things together, say. That's one way we can do things. But it would be just as feasible to run a distributed execution engine for our map plus reduce framework. In that case, say we have all our data maybe on a master node. We distribute it out we sort of split the data up now into multiple different shards, and we send each to a worker node. This could be different nodes. They could be just different maybe cores on the same machine. It really could be anything. They could have well, for simplicity, we'll think about it actually, actually sending the actual data, but they could, have the data locally already on their machines and then just read it there instead of actually splitting it up from the master. But we take one worker, and I apply my mapper, so that applies my function to each of the elements in this list, just the ones that it has in its own machine. And then I apply, for instance, the reducer, but I do it locally. So I first take each machine and I apply the reducer. So say I'm adding up the elements that just occur on that one machine, and that gives me one value for that machine. And now in sending back data, I only have to send back that one number to the master, and then I apply the reducer one more time, and I get the final value, which is going to be the sum of all or whatever function you want to compute of all those elements of the data. This is conceptual, but it kind of illustrates the point that the programmer does not need to know or care about this framework when they write a MapReduce task, right? It would be the same mapper and same reducer function that you write, regardless of whether you're executing it in this framework versus that one up there. That's very, very powerful, and it leads to less bugs, leads to less everything that a programmer can do, and so was a really big win for the distributed computation kind of community and the idea of distributed computation. Incidentally, you probably don't want to do this thing exactly like this if you're actually running it, because remember what we said about network speed being slower than disk speed and everything else, and computation is like the fastest thing of all of them, right? If my data fits all on RAM in one machine, and these are actually different machines now, this is an awful idea. Because what I'm doing is I'm splitting up my data. Well, actually, I take it back. It's an awful idea if the mapper and reducer are relatively fast. If the mapper is genuinely a really hard problem, like maybe it really is like I have to solve some combinatorial problem on each individual element where I really want the benefit of computation, then fine. But if this mapper and reducer are fairly fast, then the bottleneck of this execution engine is going to be actually sharing the data, right? Sending the data over the network. And this is exactly the kind of things you were seeing in that single thread versus these distributed computational frameworks in the first slide I had. Namely, when you have this overhead of network communication, all these kind of things, you're often much worse off than if you just executed everything on a single machine and took a little bit longer in terms of your compute time. So be aware of that. This actually, for a lot of settings, would be slower than doing it on a single machine and just running it a little bit longer computation-wise, but having much less, say, network usage. But again, supposing maybe I suppose the data is local on the workers already or something, then maybe it's going to be a benefit. And again, programmer does not need to worry about how these things are actually laid out. Okay, any questions? Yeah.
So the study you mentioned, it considered like sharding the data first.
I actually forget if it sharded it first. I think they were pretty fair comparisons, so that would seem rather unfair to me if they sharded it first. They might have either been on one single core, a single machine, or they might have actually already distributed the data ahead of time. I think it was this was I believe it was a very fair comparison, and if they were talking about sharding time, then that wouldn't be very fair. But you might want to read the paper to verify that.
Also, a lot of times, like, the data is just naturally distributed.
Yeah.
So in that case, it just makes sense to kind of write, map.
Exactly. In fact, I would argue that it almost, so the question was, or the comment was, a lot of times the data already is kind of naturally distributed. If you have a database that's storing it in a distributed fashion, as single requests come in, you're logging things on different machines, or different machines are just collecting different logs. The data already is on different machines, and so it's very natural to think about doing a distributed computation to compute based upon that. However, that's not always the case. So a lot of times data is not on many machines, and in that case, when it's already not on many machines, you have to think about the overhead involved in splitting it across many machines. So you have to be careful in both cases. I mean, if they're already there, it may sometimes still be faster to do a one-off query to get it on a single machine, analyze it there, and then send it all back. Or the opposite could be true. It could be better just to leave it there, do the computation there, and come back. It really is going to be dependent on the type of computation you're doing, just how much data you have, and kind of what the constraints of your particular problem are. Yeah.
Is there a metric or some sort of like accepted practice for the number of redundant computations you're doing for when you're doing this MapReduce, or against certain machines failing?
Is there a metric for? Sorry, I can't quite follow.
You have work from 1 to n.
Yep.
So instead of having this work running like work 1, let's say work 1 is doing work 1. Instead of having work 1 running just on work 1, let's say it's a single machine, have it running on 2 machines. So instead of 100 machines, you need 2. Like instead of n machines, you need 2 n machines, or something like that against very frequent hardware failures. I don't think in real life it will be that frequent. But is there such a method? Because I know that if like one computation fails, everything waits for that to complete.
Right. So I think the question was sort of long, but I think it got down to the question of, are there metrics that sort of measure the trade-off between extra computation versus the probability of a machine failing and things like this. So in general, a lot of the things just will boil down to timing results, right? Because ultimately, what you want is things to work fast, and you want them to work, with assuming that they are fully reliable, you want them to work fast. So, for example, there will often be studies that show that when you have redundancy, they can account for some workers being slow. But if you take that out, you don't have that, and so therefore, with a little bit of additional overhead and sort of computation, you get a 30% speed up in time or something like that. With 4% more computation. So I think it boils down to, there are a lot of metrics. Some people measure just like power it takes to do these things. So how much computation do you get per power, per unit power, per watt, right? Or energy, or total energy, right? But oftentimes this boils down to kind of the raw time it takes to execute tasks that are fully reliable. Yeah.
So when you're talking about redundancy, when it is there, so does the execution engine take into consideration like the speed of the worker, or whether data is clustered?
Yeah. Yep. So I think the question was what does the execution engine have to do to a certain extent, right? Does it take into account all the locality? And then the answer is absolutely yes. So it is the job of the execution engine to worry about nodes going down, to worry about if a node's taking a long time, do I want to take that same data and just run it somewhere else in my network? How do I make sure that most of my data is already there when I start a task? And this is why Hadoop is not a 2-line program, right? Hadoop's it's a lot of code, right? And actually, Hadoop, the MapReduce part is actually very tightly connected with their file system, which is a distributed file system that already shards out data along multiple partitions on different machines. So they're all very tightly connected. And the key point is that, yes, the execution engine kind of worries about all of that. That is what handles all of these things. That code has to deal with all of it. I mean, someone has to deal with all of it, right? But you as a programmer writing a MapReduce task don't have to worry about any of it. Okay, so now we've talked a lot about map plus reduce. Let me switch gears and talk about MapReduce. As I mentioned, MapReduce was a tool developed in Google in the early 2000s. And it's not the same as map plus reduce. That's very important. It's not that. But it's very similar. In fact, you can kind of think of it, and this is kind of but the paradigm that it is. This is how it's defined. It's similar to map plus reduce, but it's not the same as those raw functions. But you can think of it like map plus reduce kind of by key. And I'll see in a second what I mean by that. So there's this very fundamental notion of keys in MapReduce, and things are with the same key are grouped together for the different phases. So in particular, there are two main differences between map plus reduce, as I defined it already, of those sort of basic primitives, and the MapReduce framework. So the first one is that the mapper function in MapReduce does not return a single item. Does not return a single thing, which is the application of that function to that element in a list. It returns an entire list of key value pairs. And I'll talk about what I mean by that in a second. We'll have a lot of examples that'll hopefully make it more clear. So the mapper, for a given single input, will return a list of key value pairs. And then the execution engine, before it calls the reducer, will take all those collections of key value pairs, and it will group them by key. So to the reducer gets a key and a list of all the values over all the map tasks that had that key. At least in the sort of conceptual paradigm of MapReduce. Of course, there are some other ways you can speed it up in practice. Okay, so this is sort of the cartoon picture of that. In map plus reduce, we have our items. We apply the mapper. We get these values, one for each item, and then we reduce, and we get one output. In MapReduce, we take a single item, and we produce a list of different keys and values. The keys can be there can be multiple keys that are the same. So each individual list the mapper generates can have multiple keys that are the same, and there can be shared keys over multiple different mapper executions. So we generate lists of keys and values, and I'm indicating what key it is by the color of the key here. And then before the reduce step, the MapReduce execution engine will group these keys together. So it will group the values together rather by key. So it'll take all these things that were created, all these lists that were created, and it will create one instance of all the green keys and all those values, and then another instance of all the yellow or orange keys and all those values. Okay? And then the reduce function is applied now to each of these individually. So you'll apply a reduce function, but the reduce function takes as input this whole list of values here and produces some output, and then it takes this whole list of values here and produces some output. So that's actually another difference between map and map, the normal reduce, is that the reduce function in MapReduce actually takes as input a key and a list of values and produces a key and some reduced version of that list. I'm not quite sure why they use the same words as MapReduce when reduce is kind of standard to be different from this, but this is what MapReduce means. This is what the mapper and the reducer do in the MapReduce setting. Yeah?
The mapper treats every individual as the same thing. How does it produce?
Sorry, what was the question there? I didn't quite hear.
Treat every item as the same thing.
Yep.
How does it different?
So the question was, if the mapper is, each mapper can only see its given item, right? It cannot see other items. How does it produce the right key? So I think that'll become clear when I talk about what those keys actually mean. The keys are not some sort of global key of this thing, though there's an extension where you actually can have inputs that also have their own key. It's a different key than the output key, but these can have their own keys, but let's forget that for a minute. Those keys usually mean something different. That they're not like an identifier of this. They're somehow some other notion of something being computed on this item here, and that's how they sort of are created. So they have to be created in a way where they can be created from a single item essentially. There's a question over there. Yeah.
Then the item 1 is processed by one instance of the thing. The item 1
Yes.
is being processed by some instance which gives value 1 and value 2.
Yes, item 1 is processed and outputs this whole thing. A key, a value, and a different key and a different value.
Can that instance give 2 values with the same key or the...
Yes, so the question was, can this one here, can this output have 2 values with the same key? And yes, it can. They are not dictionaries, they are just key value pairs, and there can be multiple keys that are the same both within here but also within a single list. Yeah. Okay, so I'm going to now give an example about how this works, and I'm going to use the first example you always see in MapReduce, which is word occurrence count. I should emphasize it's not just word count, 'cause that can mean that's ambiguous. Let me change that title. Word occurrence. So this isn't just counting the total number of words, it's counting the number of times each unique word in this text occurs. All right, so we have some text here. The text is assumed to be split up by lines. So each line in that song is a item that we pass to a mapper. This was an example on some website for MapReduce, and once I heard it, I couldn't think about any other example. So as you saw from last time, I have a 2-year-old, and so this thing sticks in my head as a great example for MapReduce because it has a lot of repeated words you can really use, showcase the power of this. Okay, so we have this in this song here. Each line is the item. So the lines are the items themselves. So if we think about a whole list, each element in that list would contain one line in that song. Then we apply the mapper. Remember, what the mapper outputs, each mapper task outputs itself a list of key value pairs. So in this case, the key that we are emitting is just the word itself, and the value is just the number 1. Right, and I'll show how that will all work in a second. But in every case, the key that we emit, and we, like I say, we can have multiple ones. So this first line here has the twice. So it has the key the value 1, the key wheels, the value 1, the key on, the value 1, the key the, etc. But the is twice in there. That's what the mapper outputs. Now, behind the scenes, the execution engine, so this is not done by the programmer, but the execution engine will take this collection here, kind of jumble them all together, and group them all together, group similar keys together, and then give a list of all the values that correspond to that key. I'll show you the code for this in a second. It's actually quite simple, the code for this, but that's what the execution engine does, is it groups together by keys and creates a list. In this case, it's a very simple list, but this is a list of all the different values that occur with that key. They're all the same in this case, of course, because they're all just 1. But this would be, for example, the value that the list of values that the key round gets, because round occurs 8 times in that song. And then finally, the reducer, each one of these elements is now passed to the reducer function. And in this case, the reducer function would just take the key and just sum up the values. And that would then output another list of key value pairs that have the key and the value, but now where the value is a single number that counts how many times that word occurred. So this might not seem all that useful. You will in your homework go through a lot of other examples, or if you want to do that one, you'll go through other examples that you can do with MapReduce. So I'll kind of leave it to that to think about more interesting examples. But there really actually are a lot of things you can do in this framework. You can do matrix multiplication this way. You can do things like creating a graph If you have, if you know, my inputs are web pages, say, and my outputs are, actually that's probably a bad idea because web pages only be for one web page. If my inputs are, you know, if my inputs are some list of pairs, then you can create kind of a weighted graph by seeing how many times, you know, this one points to this one, and you can do all those kind of things that sort of seem actually quite difficult, but are actually pretty easy to implement in this framework. I think in the homework you will actually implement, among other things, k-means using a MapReduce framework. So in that case, the mapper essentially assigns the points to clusters, and the reducer would take the cluster indicator being the key, and then would take the mean of all those things. So k-means is kind of a nice algorithm for thinking about how you would apply MapReduce. So let's see what this looks like from the execution engine standpoint. So here is the execution engine for MapReduce, or well, not but a simple execution engine for what, you know, the task is actually running. So MapReduce takes as this MapReduce function takes as input a data list. So that's a list of the things you're going to operate on, a mapper function, and a reducer function. And the first thing it does is it runs, just like before, it runs the map function, runs the mapper function on each element of data and compiles a new list, which I'm calling values here. Now, importantly, values itself is actually a list of lists, right? Because each output in the values is going to be itself a list. That's right. That's like the values thing is the list of all of these guys. So each element in values is itself a list of key value pairs. Right? And now we do this grouping. This is actually the hardest part for the execution engine. We have to do this grouping by key. So I'm doing that. You can do it more efficiently with other methods, but I'm doing it kind of the pure Python way. I'm creating a dictionary called groups here, and I'm going to iterate over all the items and values. So each items, remember, the values in the items and values are itself lists. So this is saying for items in values, items would be one entire row of that list there. Right? So now I have my items, and then for each key value pair in items, that will iterate over each grouping of key value pairs. If the key is not already in groups, then I add it, just a new list with just that one value. If it's already in there, then I actually append that value to that groups for that key, right? And this part up to here is what would create this output. So groups is actually a dictionary where these are the keys and those are the outputs. And these things here are the values. And then finally, I get my final output by applying the reducer function, and I pass both the key and value pair in the reducer for all the key value pairs in my dictionary. So here, for example, is how you would call MapReduce. Here's how you would write your mapper and your reducer. My mapper just will return a list of word and one for all the words in the line. So I create a list here that has word and one for word in all the elements of line. And my reducer is just I keep the same key as before and I sum up the values. And if you make lines, you know, your thing here, and you execute it, and you run this code exactly, and you'll see what it does. It gives you this, not surprisingly. So the question was, is the grouping implied? What do you mean? What do you mean by implied?
There is no explicit group by.
Absolutely, yes. So this is really important. Is that the MapReduce execution engine is what does the grouping. You do not, as a programmer, do the grouping. You output keys for each item, and the engine will do the grouping for you. This is sort of actually this is a really key point about MapReduce. MapReduce will always do this operation of grouping by keys. So you emit key value pairs, a bunch of them in your mapper task. It will take all of those, it will group them all together by the key, And then in your reducer, you will have, for only a single key, all the values from all my tasks that corresponded to that key. And that is always how the pure MapReduce works. So it's not just sort of the map and reduce function. This is why it's different from just map and reduce. But with this extra element, it's kind of, you can think of it kind of like map and reduce by key. So grouped by key. And that's very useful because it's not trivial to just think how you would, I mean, you could, but it's not obvious to see, for example, how you would do word occurrence counts in a pure map plus reduce framework. I mean, you could do it, but you have to kind of do it. It's not obvious to see how you would do it. You have to sort of simulate the grouping yourself in the reducer or something, or I mean, right? You have to sort of in your reducer, you have to build up a mapping, and then you're just iterating over the list anyway. So what are you really doing, right? So it's really important that this group by key is a core operation to the engine itself, not to what you write. You write the map and reducer, the engine does the grouping. Okay, so that's actually all I'm really going to talk about. If you want to see more about, I mean, in terms of the details here, if you want to see more about how you use MapReduce, you can do the homework on MapReduce, I hope, or you can do it for extra credit too, or take a whole course on MapReduce. But I will mention that there are some more advanced usages than this. This is a really, I mean, word count's the simple, silly example everyone always gives for MapReduce first, and it's good, I think, to think about the grouping by keys, etc. But of course, it's not really what you want to do in practice. A couple key sort of points I wanted to make, though, is if you read or sort of use a MapReduce library, you will often see the inputs themselves also being key value pairs, and that's actually more standard. So it's standard to have the inputs also have keys to them. You're free to ignore those or not. In the word count case or the word occurrence count case, you would just ignore them, but you could keep them. The other thing is that, and sort of this is kind of related, but separate too, is that many real cases, you actually have to chain together multiple map and reduce steps. So maybe you count your words, but then the last step you find the word that occurs the most in your document, right? So that's actually would become another reduce step after your last map step. You do a further after your reduce step. You do a further reduce that uses based upon like a min operation, right? So you can do all of those things sort of nicely with MapReduce, and in fact, most MapReduce frameworks actually have the ability to do multiple maps and multiple reduces, and you have to iterate these things to really accomplish much of anything. I think all the examples we have are still just going to be one map and reduce. I guess the exception would be k-means, where the whole point is that you do it multiple times, right? So one iteration of k-means is kind of like a MapReduce step, but multiple iterations are going to, of course, be multiple iterations of the MapReduce step. You'll probably see this word too, something called combiners. So combiners are just sort of like local reducers that run right after the mapper phase. So it seems a little odd, right, that, thinking about memory bandwidth, right? In this case, because the grouping by key has to happen sort of globally for all the machines, it seems kind of a waste to say, send the twice. I should just instead send the with the count 2 as to my grouping by keys. And that would get the exact same number, right? I would just have take out one of these here and have a 2 there instead, and I can do that for all of them. So this is often done with something called combiners, and combiners are just sort of like reducers that run locally on each machine after the map, directly after the mapper step. So they're kind of a pre-process, a pre-reduce that saves a lot of computation in the end. And you can do, as I said, also you can be fancier and create like a tree of your mapper of your reducers to make it more efficient, things like this. There also are times where you need the optional ability to also share additional context with all your mappers. So this is actually important. Consider again the k-means case. I probably should, well, it's a homework, so I don't want to give too much away. But in k-means, for instance, in order to know which cluster you assign each point to, you have to know what the clusters are. And that's shared across all your mapper tasks, right? So there's also, you need the ability sometimes to share. And importantly, it's read-only, because you can't change those within a mapper task. Then you'd have all sorts of the normal race conditions, stuff like this, within a parallel computing engine. But you want to have some context that all the mapper tasks share, that they can all read in order that they can make similar decisions for all the different points. And that's usually called some sort of shared context between the different mappers or reducers. Okay, so that's actually kind of all I'm going to say technically about MapReduce. I'm going to make a few kind of broad statements now. And the first is that MapReduce is not popular because of how powerful it is. It's popular because of how unpowerful it is in some respects. What I mean by that is MapReduce, by its definition, is restricted, right? You can only have 2 types of functions, and there are tons of times where you want to communicate from one mapper to another, and you can't do it. I mean, you can try to fake it with other things, but you can't do it natively in real MapReduce code, right? So it limits what you can do with your sort of programming paradigm, which is actually a great thing, though, because parallel computing is one of the hardest things for humans to get right, for programmers to get right. When you start talking about running, multi-threaded or even multiple machine programs, programmers just have a very hard time doing that correctly. And so what MapReduce does is it puts a pretty strict barrier about what they cannot do. This is great because it lets people that don't really know how to write parallel code write reasonable parallel code, or things that at least run kind of okay sometimes. And I think this is actually what made it take off so much. It's kind of this almost minimum set of operations you need to do useful things, and you can do very useful things in it. I mean, you can run PageRank, you can run these, well, sort of, kind of PageRank. You can run word count. You can create web links. You can do this kind of stuff. You can trace links. You can do all these really, really nice things, yet at the same time, so it's sufficient to do some interesting things. Yet it is also not too complex to the point where you just are going to take too long to write your code. You can just focus on getting your work done instead of writing complex parallel code. And as I said, because this is just elaborating on that, but the end user just has to implement these 2 functions, the mapper and reducer. No worries about inter-process communication. No worries about resiliency. No worries about how you group by key with the most efficient way of sort of doing that, the right data structure to use. You don't worry about any of that. You just return a bunch of key value pairs, and things, if you're doing it right on the back end, tend to kind of work okay. So that's why it's so popular. It's because it makes parallel computing relatively easy. Now, having said that, there are some huge downsides to it as well. And the first one is sort of based more upon traditional MapReduce, but and this is actually one of the big things that has been fixed, or at least addressed by new frameworks in recent years. And that is that MapReduce, at least in its traditional sense, is extremely slow. So the way MapReduce is usually run is that every time you run a mapper task or a reduce task, you take the input, you read it from disk, you run your mapper, and you write that result back to disk. This is how you achieve the resiliency of nodes possibly going down. So first of all, the writes and reads are all redundant. So you're using a file system that is redundant, split across multiple machines. So your mapper is running. Every time it runs its task, it reads its input from disk, writes it back to disk, and it really writes it to multiple disks at the same time. So if that machine dies, where that mapper is running dies, it doesn't actually matter. The data on that one machine maybe is gone, but you have it elsewhere. You just start up a new task running that same exact mapper on a new machine where that data was. And you can chain together very, very long chains this way. My k-means can die midway. One machine can die midway through my k-means, but I still have all my input and output from the previous iterations on there. So I can still just run kind of as expected. But again, the point being that the way it does that, the way it gets that level of resilience to, say, machines failing, is that it reads and writes from disk every single, before and after every single thing it does. And this is one of the huge bottlenecks of MapReduce. And in fact, this is really what, so another framework called Spark, which was a sort of a successor in some sense, or has, frankly taken over most of the popularity of traditional Hadoop MapReduce at this point. the big thing they did is just they said, well, let's not write to disk between different things. Let's just keep it all in memory. Now, of course, that's actually hard to do and maintain resilience too, because if a machine dies, now you have a whole bunch of memory that sort of you can't recover from before. So how do you do that? They do it by persisting actually a graph of computation that led to that data. But you know, it's relatively speaking, it's relatively simple. The big idea, we're just going from disk only in traditional Hadoop to disk and or mainly storing things in memory. So you know, some of these things have been addressed a little bit. The second problem is sometimes you just really do want to communicate between a couple nodes, or have one node see something in the data, and you want to send a message to all the other nodes without waiting for like a reduce and a context sharing to happen. And so a lot of the frameworks like Spark, other things like GraphLab actually is a slightly different compute paradigm, so I won't go into that. But tools like Spark actually also slightly expand the allowable class of operations from just MapReduce to a slightly larger set. You have a few more things you can do, different types of reduce, different types of ways of sharding data, stuff like this. You do have more ways of doing this than just the map and reduce. However, even with all these advantages, all of these things, and again, this harkens back to our first point, the scalability at West cost paper, all of these things will be slower because they, by definition, have overhead in trying to communicate multiple things and trying to do that group by key. They will be slower than doing it on a single machine if you can run all your data on a single machine. Just almost by definition, they will be. I mean, again, there's some cases where that's not the case, where you have, 1 gigabyte, but it's still faster to run on many machines. That is actually the exception rather than the rule. It usually is not the case, unless you're really sort of heavily compute heavy in your mapper task. You probably will not be faster by running it on multiple machines. All right, so last statement is that when you use MapReduce in practice, you fortunately, as I said, don't have to deal with any of this stuff. You have to just write your mapper and reducer tasks. And don't write it like I showed it either. Use a framework. One of the more popular frameworks in Python is something called MRJob. I don't know if it's pronounced Mr. Job or just MRJob. But it stands for MapReduce job, so I don't know if it's Mr. Job or MRJob. Actually, just seen it written. But essentially, this is sort of a nice wrapper that lets you easily write MapReduce tasks. It lets you also chain together multiple MapReduce tasks in a whole graph of computation, and then it lets you actually also run it on sort of seamlessly either on a Hadoop cluster or on Amazon's Elastic MapReduce or on Google's cloud, and so it's fairly nice. I actually wanted to use the MRJob or Mr. Job library for your homework, but unfortunately did not install on the AutoLab computers for some reason. I don't know why, because it can run locally, but didn't install on the AutoLab computers. So we have our own MapReduce, which we took from some code somewhere and modified slightly for our purposes. And so you'll be using that instead of MRJob. But if you actually wanted to use MapReduce for real, the homework's great because you actually can see how it's executing it. It uses multiple threads or multiple processes on a single computer, but still not multiple computers. But if you want to see how sort of you can go about really running MapReduce jobs, I would check out MRJob, the library. And that's how you probably want to do it in practice anyway. All right. As amazingly, I actually finished 2 minutes before the end of class. Are there any questions? No one wants to say, because this is like the first time we've ever ended early by 2 minutes. Wow, I really should have talked more. That's clearly my mistake. All right, so everyone have a good Thanksgiving. No class on Wednesday. We're back next Monday. Everyone has a safe and fun Thanksgiving, and I'll talk to you all soon. All right.